All right, if we go back and remember our uniform circular motion equations for velocity, so when anything is spinning around in a circular motion, we can calculate its velocity, just like we can if we were in a traveling in a linear motion. In a linear motion, we know that the velocity, or let's go speed. Speed equals distance over time, right? Meters over seconds is meters per second, which is speed. So velocity is nothing more than speed with a direction associated with it. So velocity equals distance over time. Now, if we're going in a circular motion, what's the distance around an entire circle? Well, the distance is its circumference. So circumference over, that's a pretty crummy looking thing. So velocity, let's get rid of this whole thing. Velocity equals circumference over time. We know that the circumference around a circle, circumference equals 2 pi r. So we can plug in 2 pi r for the circumference, and the time that it takes to go around a circle, we know now as period. So we can put that over period. So we get velocity equals 2 pi r over t, and that's our first equation. Now we also can break this 2 pi r over t. That would equal 1 over t times 2 pi r. Right? And we know that frequency equals 1 over period. So we can put in frequency for 1 over t, and we now have velocity equals 2 pi r f. This equation. Moving on. An object's in circular motion. The radius of its motion is 2 meters. Radius is 2 meters. Let's write our givens. And its period is 5 seconds. What is its velocity? Velocity is our unknown in meters per second. So we know we have our equation velocity equals 2 pi r over t. We can solve that and plug in our values, and we get 2.5 meters per second. Now we have a problem where an object's in circular motion. The radius of its motion is 2 meters, and we're given a frequency this time, not a period. What's its velocity? Well, we use the other equation. Velocity equals 2 pi r f. Plug in our values, and our answer is 101 meters per second. Simple harmonic motion and uniform circular motion. There's a whole lot these two have in common. We can see that if something's going in circular motion, it has a periodic motion where it's returning to its same position over and over again. If we have a mass suspended from a spring, you know it's going to be bobbing up and down as well. So we know that one cycle in circular motion is pretty easy to figure out. We could say, okay, we're starting here, and when we get back to that one point, that's one cycle. But how do we do it when we have a mass that's bobbing up and down on a spring? Well, we kind of say, all right, if this is all the way down as far as it could possibly stretch, it's going to go up to its equilibrium position where it's not stretched or compressed. Then it's going to continue traveling until it's fully squashing the spring. It's going to next come down back to its equilibrium position, and finally where it started. When it returns to where it started, that's one cycle as well. So if it takes 4 seconds for a system to complete one cycle of simple harmonic motion, what's the frequency? Well, we know frequency, 4 seconds to complete one cycle. 4 seconds to complete one cycle. That's a period, right? So 4 over 1, it's 4 seconds. So frequency equals 1 over period. So 1 over 4, our frequency would have to be 0.25 hertz. The period of a mass spring system is 4 seconds. And the amplitude of its motion, there's something new. The amplitude of its motion, that means how far What's the maximum this thing will travel from the equilibrium? And they're saying that's a half a meter. So amplitude is 0.5 meters. How far does the mass travel in 4 seconds? Well, in 4 seconds, it has a period of 4 seconds, which means so period is equal to time over n. So it's in 4 seconds, it's going to make one cycle. So if it starts here, it's going to go up, down, down again, and up. And this is when it's back at its original starting position. They said the amplitude is a half a meter. So it's going to travel a half a meter up, a half a meter down, a half a meter down further, and then a half a meter to get back to its original position. So its distance that it's actually traveling in 4 seconds is going to be 4 times that 0.5 number, and that should be 2 meters. So given the same period and the amplitude, how far does it travel in 6 seconds? So this time around, it's going to be starting here. It's going to go up, down, down again. And now we're at 4 seconds because that's a period, right? But now we're traveling half a period further. So it's going to go up and down again. And we mentioned its amplitude, which is its maximum displacement, is a half a meter. So it looks like we have, what, 6 of these? 1, 2, 3. So 6 times a half a meter, it looks like it's going to travel 3 meters.